something important just happened where none of us could watch it directly. On October 29, 2025, at 7:47 in the morning Eastern Time, an interstellar comet nicknamed 3I Atlas reached its closest point to the Sun. A few minutes later, it slipped into the Sun's glare and vanished from view for 8 days. Ground telescopes were blind. Even our largest space-based mirrors had to wait. Whatever happened in that window, the visitor experienced it alone. Right before it disappeared, the comet changed, and it changed fast. Its brightness did not rise in a smooth, gentle curve. It jumped. The increase was sharper than simple warming can explain. At the same time, the light shifted toward blue. That is the strange part. A comet should be cold. A cold surface reflects sunlight or glows faintly in redder tones. This looked different, as if the gas around the comet was making light, not just bouncing it. When 3I Atlas emerged from behind the Sun, early tracking showed a normal path. No sudden turn, no dive toward Earth, just a clean loop and onward. But there were gaps in the record, images we expected but had not been released, instruments that paused right when the action was strongest. Those gaps leave room for questions, and questions are where good science begins. Here is how we will tell this story. We will stick to what can be tested. We will move step by step. First, where a traveler like this could come from, and why its age changes how we think about it. Then, what happened near the Sun, and why the color of the light matters. After that, we will weigh the most likely explanations, starting with the boring ones, before we touch anything extraordinary. For now, hold one picture in your mind. A small body, only a few kilometers wide, wrapped in a cloud that swelled to hundreds of thousands of kilometers, brightening hard, leaning blue, and then slipping behind the Sun. That is our starting point. Now, let us talk about where this visitor was born, and what that origin can tell us about everything that follows. This is not just a traveler from another star. It is probably a traveler from another time. The material inside this object looks to be around 10 billion years old. Our Sun, our planets, and every familiar thing in the sky around us are about 4.5 billion. So this visitor formed long before our solar system existed, before Earth, before the Moon, before the dust that became us had even gathered. Why does that matter? Because time is cruel to small bodies. A typical comet is a loose mix of ice, dust, and rock. As it falls toward a star, the surface warms, the ices turn to gas, and narrow jets burst from cracks like tiny geysers. Over many passes, the shell weakens, the shape slumps, and some comets split in two. That is the usual story. But this one crossed interstellar space for eons, wandered through harsh radiation and tiny impacts, dipped close to our Sun, and still arrived active. Whatever it is, its structure is tougher than the dirty snowball picture most of us learned. Interstellar is a simple word with a big meaning. It does not belong to our Sun. It was born around another star, then thrown out, most likely by the gravity of a giant planet, into the dark between stars. From there, it drifted for ages. Think of it as a sealed package from a coast we have never visited. If we can open that package with our instruments, the grains inside tell us about the waves, the rocks, and the chemistry of that distant shore. This is why astronomers care so much. We almost never get samples from other star systems. We cannot fly there yet, but sometimes the samples come to us. When that happens, we bring everything we have. Cameras track how fast the brightness changes. Spectrographs split the light into thin lines so we can read which gases and metals are present, almost like scanning a barcode. Polarimeters tell us how light scatters off the dust, which hints at grain size and surface texture. Radio and plasma instruments watch the solar wind, the steady stream of charged particles from the sun, slam into the gas cloud around the comet. Put together, these tools build a clear, testable picture of what the object is made of and how it behaves. And here is where this story bends. From the very first measurements, a few things did not sit right with the usual rules. The path lined up closely with the flat plane where our planets orbit. The timing placed it near Mars and then hid it behind the sun during a critical window. And for a while the gas seemed to flow in a direction we do not expect. None of that proves anything wild, but it tells us to slow down, look again, and be careful with our assumptions. Next, we follow those early signs, what happened first, why they matter, and how they set up the burst of light we saw near the sun. When this visitor crossed into the inner solar system, everyone expected the usual pattern. Come in from a strange angle, warm up, vent gas, and head back out. Instead, it slid in almost along the same flat plane where the planets orbit, as if it were already riding the track our system uses. That does not prove intention, but it is rare enough to make careful people look twice. The timing added more questions. As it moved inward, it passed close to Mars, close enough that orbiters around Mars could have taken sharp images, then kept going until, right at its closest approach to the sun, it slipped directly behind the glare from Earth's point of view. For 8 days, our best instruments could not watch it. That is an inconvenient moment to lose sight of a fast-changing object. And then there was the tail. Everyone learns the same rule. A comet's tail points away from the sun because light and charged particles push dust and gas outward. For several weeks, this object showed a jet that seemed to aim sunward. At first, some blamed the camera angle, but different observatories from different positions reported the same thing. Then, quietly, sometime in October, the behavior ended. The tail flipped back to the normal direction, and the comet carried on. None of these signs, by themselves, prove anything dramatic, but together, they say this is not a standard case. Path alignment, awkward timing, and a tail that broke the simple rule. Those are reasons to pay attention. The real surprise, though, was still ahead. Near perihelion, the brightness did not just rise, it surged, and the color leaned blue in a way that suggested the gas itself was making light. That moment is the turning point. In the next part, we will stay with the measurements and explain what bluer than expected actually means, why a giant halo formed, and how emission can change the whole picture. Right before the comet slipped behind the sun, something happened that forced everyone to check the numbers twice. The brightness did not rise in a gentle curve, it spiked. Multiple spacecraft saw the same thing from different angles, a dim glow swelling into a huge halo around the nucleus, a cloud of gas and dust stretching hundreds of thousands of kilometers. For an object only a few kilometers wide, that scale is extraordinary. The shock was not only how bright it got, but what kind of light we were seeing. A normal comet mostly reflects sunlight. Sometimes it glows a little from heat, which skews redder because the surface is cold. Here, the color leaned bluer than expected. When instruments split the light into its components, they found a strong hint of emission, light being made by excited atoms or molecules in the gas, not just bounced off dust. Think of the difference between a mirror and a light bulb. Most comets behave like mirrors. During those hours near perihelion, This looked more like a bulb. Why would that happen? The simplest path is chemistry plus sunlight. Different gases light up at different distances from the sun. Some, like carbon-based compounds, can fluoresce, absorb ultraviolet light, and re-emit it at specific colors. If this comet carries an unusual mix, and if it has very fine dust that scatters short wavelengths well, the overall color can tip blue. Another piece is the solar wind, a stream of charged particles from the sun. When that wind hits the gas cloud, it can strip electrons and let them snap back, which creates narrow, bright colors. If the cloud is dense and wide, those tiny reactions add up. One more clue came from the texture of the halo. It did not look perfectly smooth. Some images showed layers or shells, like waves inside the glow. That points to jets turning on and off as the comet rotates, or thin crusts cracking in sequence and releasing pockets of gas. It does not require a hidden engine. It fits the idea of a complex surface waking up under strong sunlight. The key takeaway is simple. During perihelion, emission from the gas became strong enough to change the overall color balance. That is rare, but not impossible, especially for an object with unusual composition and very fine dust. Then came the clean before and after. Before perihelion, the odd sunward jet. During perihelion, the surge, the giant halo, the blue-leaning light. After it emerged, the tail looked normal again, and the path stayed on track. No sudden turn, no obvious thrust, just gravity doing its job. When a result does not match the handbook, science gives us three doors: bad data, bad model, or something new. Multiple instruments agreeing makes the first door less likely. That pushes us to compare our models to the data, and only then consider anything beyond them. In the next part, we will open those doors one by one, plain language, no drama, and see which explanations still stand once we test them. When results do not fit the handbook, there are only three doors to try. The first door is simple. The data is wrong. Maybe a sensor saturated. Maybe the angle fooled us. Maybe a filter shifted the color. That happens. But this time, different spacecraft, using different cameras from different positions, all told the same story. The early sunward jet was real. The brightness surge near perihelion was real, and the color leaned bluer than expected. When independent systems agree, the bad data door gets smaller. The second door is more interesting. The model is wrong, or at least incomplete. Our mental picture of a comet is a soft snowball that warms, steams, and fades. Real comets can be messier. Surfaces are patchy. Layers crack at different temperatures. Jets switch on and off as the body rotates. If the mix is unusual, say low water, but richer in carbon dioxide or other volatiles, plus very fine dust that scatters short wavelengths, then emission lines and blue-leaning light can grow strong. Add the solar wind, a stream of charged particles from the sun, slamming into the gas cloud and knocking electrons loose. When those electrons snap back, they make sharp colors. If the coma is large and dense, those tiny flashes add up. Even the strange jet can live here. A vent near a ridge, a cavity opening on the sunward side, or a rotating nozzle that sends gas forward for a while before the surface changes and the jet flips to normal again. None of that needs anything exotic. It just means our model must stretch to cover a rarer mix of chemistry, texture, and timing. The third door is the one people jump to fastest, something genuinely new. A hidden heat source, a designed system, an object built to endure for ages and recharge near stars. It is not wrong to ask. It is wrong to start there. The rule is clear. You do not open the third door until you have pushed hard on the second. Right now, the second door still holds a lot. Chemistry can explain the color. Rotation and cracking can explain the halo structure. Changing vents can explain the tail. The path stayed clean. No thrust, no course correction. Gravity did the driving. So why are we still watching closely? Because this object sits near the edge of those models. The age looks ancient. The mix looks unusual. The timing was awkward. When many rare things happen together, you keep the lights on and you keep checking. That is how science avoids easy answers and still catches big ones. Next, we will compare two full stories side by side. One is natural, a tough fragment from a broken world that carries strange chemistry and vents in bursts. The other is the whispered one, a machine built long ago to travel between stars. We will lay out what each story would have to explain and what evidence would move the needle either way. At this point, we are not chasing a dramatic answer. We are comparing two clear stories that could both fit the measurements. One is entirely natural. The other is the one people whisper about. We will give each the same fair test: what it explains well, where it struggles, and what new data would push it forward. First, the natural story. Imagine a fragment of a broken world, not a fluffy snowball from the edge of a system, but a dense piece from deep inside a planet that was torn apart long ago. In the early galaxy, young stars hosted crowded systems. Big bodies collided. Tidal forces shredded worlds. Core and mantle material flew out. A shard like that would be tough, with low water and pockets of unusual volatiles trapped in cracks. If such a shard was ejected into interstellar space and wandered for billions of years, it could arrive here looking like a comet, but behaving differently. This neatly covers the strong structure that survives heating, the modest water content, and a bright, emission-heavy coma when certain gases finally vent under hard sunlight. It also allows for narrow jets that turn on and off as the body rotates, and a halo that grows in layered shells as one pocket after another opens. What would challenge this story? If future spectra showed element ratios that do not match any known natural formation path, either planetary or cometary, or if we saw heat patterns that cannot be made by sunlight plus outgassing, then the fragment idea would need help. For now, it fits a lot with only one assumption. This is a rare kind of natural object. Now, the other story. Picture a machine built to last. If a civilization wanted to explore the galaxy across deep time, it would send autonomous probes, durable, self-stabilizing, and able to recharge during close passes by stars. The outer shell could be rock-like to survive micrometeoroids. Vents could manage internal pressure. The object could be designed to blend in so it is ignored. In that frame, a bright, layered coma near the sun might be a thermal management event. A tail that briefly points sunward could be venting control as the system rotates. A blue-leaning spectrum could come from engineered materials or intentional emissions. That is the picture people imagine. But the test is simple. Where is the non-gravitational motion? Where are the coherent signals? Where are the repeatable behaviors that cannot be made by passive ice and rock? So far, the path looks clean. Gravity explains the motion. We do not have verified thrust, and we do not have a signal that stands out from natural interaction with the solar wind. That does not kill the idea, but it puts it on hold until data demands it. Let us put the two stories side by side. Explains the strength and survival? Natural fragment. Yes. Dense, cohesive material. Probe. Yes, designed durability. Explains low water and unusual gases. Fragment. Yes, planetary interiors are dry and can carry exotic chemistry. Probe. Maybe, depends on materials and purpose, but not required. Explains the quick, blue-leaning burst. Fragment. Yes, volatile pockets plus fine dust and strong solar wind can boost emission. Probe. Maybe, heat management or deliberate emission, but that needs extra assumptions. Explains the clean trajectory. Fragment. Yes, ballistic. Probe. Awkward. If it can maneuver, why none now? You can say it does not need to, but that is another assumption. When answers need fewer extra steps, they usually win the first round. So, what would move the needle? 3 kinds of evidence. 1. Motion. A measured, sustained non-gravitational acceleration that cannot be explained by outgassing geometry. That would be a big shift. 2. Heat. A localized hotspot that stays warm on the night side or cycles with a pattern not tied to sunlight. That hints at internal power. 3. Signals and structure. Narrowband radio, regular pulses, or geometric surface features that repeat with the rotation in ways natural fracture patterns do not. Any one of these would demand serious attention to the artificial path. On the other hand, if upcoming spectra show ordinary mineral bands, if the blue emission is matched by known fluorescent lines, if the coma dynamics track cleanly with rotation and sunlight, then the natural fragment wins by being both simpler and complete. There is also a human rule worth stating out loud. In science, exciting is not the same as likely. We start with the explanation that uses the fewest new assumptions and matches most of the data. If that fails, we add assumptions carefully. That is how we avoid fooling ourselves and still leave the door open for a genuine breakthrough. Where does that leave us today? With a priority list. Keep measuring the path to catch any subtle push that gravity alone cannot explain. Map temperature across the surface to see if something is heating from within. Take deeper spectra to pin down the exact gases and metals in the coma. Watch how the brightness and tail modulate with rotation. Each of these tests can eliminate guesses quickly. And there is one more practical point. If this object is a natural fragment, it is still a gift. It is a sample from another system, a record of chemistry and geology we do not have on Earth. That alone makes it historic. If it is a probe, then it changes our place in the story of life in the galaxy. Either way, we win by doing careful work, so we keep going. Because the next part of this story is not about ideas. It is about missing pictures and delayed releases, what we have, what we do not, and which upcoming observations can finally close the gaps. That is where we turn next. Now we have to talk about the gaps, not theories, just what we have, what we do not, and what that means. We have space-based coronagraph images that caught the surge near the sun. We have brightness curves from more than one instrument that agree the rise was sharp. We have tracking that says the path stayed clean, with gravity doing the work. Those are the anchors. What we do not have is just as important. We do not have all the close pass images we expected from the weeks around Mars. We do not have a continuous, public, minute-by-minute record during the 8 days the comet hid in the sun's glare. And we do not have a single, stitched timeline from every observatory that watched before and after perihelion. There are reasons for missing data that are not dramatic. Spacecraft time is booked months in advance. Teams prioritize targets. Raw files are big. Calibration takes time. Some instruments pause for maintenance. Sometimes the people who took the data want to check their work before the world checks it for them. That is normal. Still, the timing creates tension. We saw the strange sunward jet, then the window where the comet brightened and the color leaned blue. Then the reappearance with a normal-looking tail and a clean trajectory. A neat before and after, with the most interesting hours sitting inside a box we cannot open yet. Here is how to think about that. Missing pictures do not change what the existing measurements already say. They do not erase the surge. They do not undo the color signature. They do not bend the orbit. What missing pictures do is limit the story we can tell about the exact how. Did the halo build in pulses tied to rotation? Did new vents open on a specific face and then shut? Did the blue emission peak and fade in steps or in one smooth wave? Those are the details locked inside the gap. While we wait, there are three kinds of updates that matter most. First, geometry. Fresh astrometry from many telescopes to confirm the path stays purely gravitational. If there is even a small, steady push that cannot be explained by venting, it will show up in the math. Second, spectrum. Deeper, higher resolution spectra to pin down which gases were glowing when the light leaned blue. That tells us whether chemistry alone can carry the load. Third, timing. Coordinated light curves to see how brightness rises and falls with rotation. If jets are switching on and off, the pattern will repeat. One more thing about the gaps. They are not permanent. The usual path is simple. Teams process. Data gets validated. Releases come in batches. Independent groups cross-check. Then the timeline fills in. And when it does, we move from interesting but incomplete to here is the sequence, frame by frame. Until then, the best move is to stay tight with what the current record supports. The comet survived perihelion. It showed a strong, structured halo and blue-leaning emission during its closest pass. It reverted to a normal-looking tail after. The orbit stayed on track. All of that stands without the missing pictures. Next, we turn from what is missing to what is coming. There are windows on the calendar when the view gets better, the instruments get time, and even backyard astronomers can help. That is where the story becomes practical. What observations can actually prove or rule out in the weeks ahead. Here is the practical part. The moments on the calendar when the view improves, what to look for, and what those checks can actually prove or rule out. Over the next several weeks, the comet pulls farther from the sun's glare. That means cleaner skies, longer observing runs, and steadier data. Big observatories will split the work. Some will track the path with high-precision astrometry, pinpointing the position night after night to make sure gravity alone explains the motion. If there is even a small steady push that cannot be blamed on venting, it will show up as a quiet drift in the numbers. Others will focus on spectra, breaking the light into thin lines to see which gases and metals are glowing. If the blue lean came from chemistry, deeper spectra will show it clearly. Specific lines, known ratios, repeatable patterns. If it does not match the usual set, that is a real clue. Thermal cameras and infrared instruments will map temperature across the coma and the face of the nucleus. If one patch stays warm when it should cool, or heats in a cycle that does not follow sunlight, that points to energy from inside, not just from the sun. Polarimeters will read how light scatters off dust. If the grains are very fine, the blue tilt makes sense. If they are larger, we look harder at the gas. Radio dishes will keep listening, not for a message, just for anything narrow, steady, and off the usual bands of natural emission. A clean, repeating tone would be hard to ignore. Most of us are not at those telescopes, but there is still a way to help. In the pre-dawn hours, as the comet's angle from the sun grows, amateur scopes can pick it up as a small, soft patch near brighter planets on the morning side of the sky. A simple plan works. Use a sturdy mount, start wide to find the field, then step up the magnification slowly. Take short exposures to avoid smearing, stack them later if you can, and note the time carefully. Even small, well-timed pictures help refine the orbit when many people share them. If you shoot video, keep clips short and stable. Sharp frames beat long, shaky ones. What can these observations decide? 4 things, clean and simple. First, motion. A path that matches pure gravity supports a natural object. A sustained extra push demands a better explanation. Second, chemistry. Spectra that match known comet gases and dust favor the ordinary. Lines that do not fit nudge us toward new processes or rare materials. Third, heat. Temperatures that rise and fall with sunlight are normal. Heat that lingers or pulses off-cycle is not. Fourth, timing. Brightness that waxes and wanes with rotation means jets switching on and off. A pattern that repeats like a machine's rhythm needs attention. The goal is not to chase a headline. The goal is to close the open doors, one by one, until only one story remains. If the comet is a tough natural fragment, these next windows will show it plainly. Ordinary physics, unusual mix, no hidden push. If it is something else, the same windows will catch the seams. A drift where none should exist. A heat map that will not follow the sun. A spectrum that refuses to match the catalog. Or a signal that does not blend into the noise. Either way, the answer comes from the sky, not from our wishes. And there is one last step after the data arrive, putting it all together in order. A clear timeline, from the strange early jet to the blue-leaning burst at perihelion, to the calm that followed, so we can say not just what the comet is, but how it behaved every step of the way. That leads us to the final part of the story. What remains after the mystery fades, and why paying attention to outliers makes science stronger, not weaker. Here is where we land. A small body from beyond our sun came in fast, hid behind the glare, lit up harder than expected, leaned blue when it should not have, and then carried on like nothing unusual happened. Along the way, we saw odd alignment, awkward timing, a tail that broke a simple rule and then snapped back. None of that forces a dramatic answer. All of it forces careful work. The next measurements will do what good measurements always do. They will close doors. If the path stays purely gravitational, that is one door shut. If the spectra match known gases and the blue comes from emission lines we can label, another door shut. If the temperature map follows sunlight with no stubborn hotspot, shut again. What remains after that will be the simplest story that explains everything we have seen. Maybe it is a tough natural fragment from a broken world, dry, old, and loaded with unusual chemistry. Maybe it asks for more. Either way, the value is the same. We learn. We refine how we think comets behave. We update our playbook for interstellar visitors. We improve the way we schedule instruments, share timelines, and stitch data from many teams into one clear sequence. That matters for the next object, and the next after that. For you and me, there is a practical takeaway. Pay attention to the parts we can test. Watch how new results change the picture. Notice when a clean, boring explanation wins on evidence, and also keep an eye on the edges where something does not fit yet. That balance is how science avoids getting fooled and still stays open to real surprises. So, we will keep pointing our telescopes, big and small. We will keep tracking the motion, reading the light, and timing the pulses. We will build the full timeline, frame by frame, until the loose ends tie down. And when the answer arrives, ordinary or rare, it will be earned. The comet will fade, as all visitors do. But the tools we sharpen here, and the habits we practice here, will stay with us for the next faint smudge rising before dawn. Keep looking up. The sky will give us the rest.